Ah, you have a lovely office.
Yeah. Yeah. Actually, I live very close to uni, just like 10 minutes walk.
Ah,
And when you have young kids, then you like office more. Yeah.
yeah,
Yeah.
it's true. Yeah.
You should enjoy them.
Yeah,
Enjoy
I
them while
enjoy
they are
them.
small.
I enjoy them, but you can't even. Sometimes you can't even write an email. Good, so nice.
Okay, Simon, do you want to use your screen in the beginning, or you are okay with Rakesh slide like this on?
I think that Rakesh can use his one.
Yeah.
Yeah.
No need for me to share my screen.
Yeah.
I just briefly give an introduction.
Okay.
Yeah.
That's good.
Okay.
Okay. Today, basically, we have a total of 61 up to this morning, the registrant. It's quite a lot, so hopefully they will log in to join live, because what I found that quite a lot of them, they register, after that they watch online, they watch through the recorded one.
Yeah. Oh. Oh, that's nice.
Yeah. So later on, I will record as well for this webinar, and then I will publish it on the website.
That's what happens when we teach. Online, only 2 or 3 students come, and then they all watch and recording. Right?
So how many subjects you are teaching this semester?
This semester I'm not teaching, because in term 1 is off for me. We have 3 terms, right?
Yeah.
So at UNSW, every academic has 1 term off.
All right.
Oh, really?
Wow.
So it can be term 1 or term 2, depending on the course you teach. So
Okay.
so this is like I can say from December to June, don't have much teaching.
This is a good strategy.
Yeah.
Yeah.
Even only October and November, only 3 months I teach, but 3 months I teach a lot.
How many subjects?
Okay.
How many subjects per year?
I can say total of 2 courses, total of 80 hours.
Okay.
Yeah.
So is it now all the lessons still teaching online?
Yeah. So I think we are going to have some labs on, in person, but the labs, if they have less number, not.
So UNSW still teach online.
Yeah, we teach online, because a lot of student numbers are very high, right?
Okay.
Numbers are very high, so I think some labs, like chemistry labs, if the total number is less, then we have some we call it like in-person labs, with following the social distancing.
Same to UTS, we have online teaching.
Yeah.
Not physical or face-to-face teaching mode. Monash, you are teaching the face-to-face?
Yeah, we back to normal.
Oh.
Wow, that's very different from New South Wales and Victoria.
Yeah.
Now what do we call it? We call it a hybrid teaching.
Okay.
So you needed to give the lecture in the lecture hall, and at the same time you need to set up a Zoom for the students who are stuck in their home country.
Okay.
Yeah, so that's why we call it a hybrid teaching.
That's more difficult because
it is difficult. Yeah,
I have experience. Some of them are from Russia, some of them are from Middle East or Latin America, India, China. So they have a time zone like 12 o'clock. You start your teaching, they already early morning, 4 a.m. and 5 a.m.
Yeah. So that's why actually all those what do they call hybrid teaching, normally actually we schedule it in the afternoon time.
All right. Also the quality of hybrid. if you have only Zoom meeting, you can see clearly, hear clearly. But sometimes hybrid, if you speak a little bit far away from computer, even though your sister,
Yeah.
it's
No,
very
no,
difficult to communicate, right?
The question is, you do need a good facility. Actually, Monash have what we call two teaching education building. All those two buildings, they has a very good facility. Yeah. So when you set up this Zoom meeting, actually the students can look at the lecture hall from the different camera.
I see.
Almost actually same. I have been there before, and yeah.
Okay.
Hey Rakesh.
Hi, Professor Wang. How are you?
Good. Hi Sean.
Hello, Santi and Dharma.
Hi, Dama.
Hey Dharma.
So we are talking about every university has a different teaching mode, online and hybrid or face-to-face.
Yeah.
Victoria and New South Wales, it's already also different from different universities.
Yeah. I went to campus yesterday, and the car park is almost full.
Oh, wow.
Yeah. It's quite difficult, to find a spot for parking your car.
Yeah. Red
So already you missed COVID-19.
red area is always available.
All right, too expensive.
Yeah. Yeah, I went back to campus for a few times a week. Yeah. Yeah, it's really hard to find the parking. So do you know how many have registered for the seminar?
65 people.
About 60 people, 60 to 65. I think 60.
Right.
I just check it.
All right.
Yep.
Sue just said most people, they register, but they watch on the recorded video later.
Right. Okay.
Yeah.
Yeah, just like a lecture.
Okay, I think we can kick start now.
Yeah. Okay. Let's start. Good morning, everyone. My name is Xiwan Zhang. Welcome to this joint seminar co-organized by ARC Research Hub for Energy Efficient Separation, MSA, the Monash Center for Memory Innovation. And today is our second webinar, and it's our great pleasure to have Rakesh and Josh from the UNSW. I think Rakesh does not need an introduction for anyone who are working as a member, particularly working on the 2D or graphene-based membrane. I think know him very well, and it's because his I think a pioneer work published in 2014 in science. In his, I think, pioneer work, it shows, the graphene can be as a promising building block to construct to the laminar membrane, and such a membrane can achieve very narrow cutoff, has an amazing size exclusion, can reject I think the molecule or ions in the water solution. And Rakesh, I think, is outstanding researcher, which is demonstrated by his a number of award of fellowship, and also very amazing publication record. And so today's talk, I think Rakesh will give I think more broad topic, and to talk about the application and the graphene oxide. And the graphene oxide, have already been discovered almost, I think, 10 years. And due to this, I think, fantastic property, I'm pretty sure actually such a beautiful material can create a very, I think, emerging application. Now, welcome, please join me. Welcome, Rakesh.
Yeah, thank you, Professor Zhang. Very nice introduction. You have some very nice, very, very kind words. I wish you were the reviewer of all my proposals. Okay, thank you very much, and really it's a great opportunity for me to present my work here in this nice series of webinar. I'm going to talk about graphene oxide mainly, and I'm doing last 6 years, 90% of my research is only in this material, graphene oxide. Okay, at UNSW we have a lot of priority research areas. So when I came here, I was introduced to this this model of what are you in these areas, which area you're going to contribute at UNSW. So I picked up these areas: advanced functional materials, nanomaterials, membranes, and alternative energy sources, sustainable materials recycling, and water purification. And other aspect of my research is all about commercialization and industry engagement. Today I thought that I can discuss a lot of my industry projects, but then I realized most of the industry projects are very confidential. So I will be telling only the basics, and then most of the work which I do with the industry is still confidential until it becomes in the public available in the public domain. But I will present the basic work. Okay, now graphene. What's so special about graphene? So I always put this slide of Andre Graham long back. He used this one, so I just screenshot this one. So graphene is the thinnest imaginable material. It's 200 times stronger than steel, most stretchable crystal, and it has a very high intrinsic mobility. And on top of it, it's most impermeable. Even helium atoms cannot squeeze through graphene like this, monolayer graphene. Now, I want to those who don't do graphene research. Whenever we say membranes, most of the time we make graphene oxide membranes, not graphene membranes. Graphene is just a monolayer of carbon atoms, but graphene oxide is also monolayer, but it has some nice properties. It has these groups, these functional groups attached to it, and these functional groups will make it possible to form in the structure of these laminates. And these functional groups are like a spacer. They are like legs of those seeds, and then that way you can make nice lamellar structure. And if you want to use pure graphene as a membrane, you need to make holes using very expensive techniques, and then scale up might be a problem for pure graphene membranes. Whereas graphene oxide is now scalable, very easily scalable material. So all my work is related to this kind of structure. These are the graphene oxide. This is, I can say, 1 sheet of graphene and then functional groups. And this is the size, typical size is 2 micron. In the beginning we used to make 2 micron, but now we make 1 micron, even 500 nanometer. We see now, we know that if you have smaller flakes, it's better for the water flux because you have more water inlets. So that way, these all our membranes are this type. And how we make it? This is one of the oldest method called the Hammer's method. We use graphite, convert into graphite oxide, then sonicate the flakes into monolayer flakes. Then the graphene oxide suspension typically looks like this. And then once you have this suspension, you can make membranes. Either you do this vacuum filtration, which is mostly I do, or you can do spray coating also. Now if you see here, this is a membrane. The membrane typically looks like this. So if you see the cross-sectional image SEM, you see all the laminar structure here. Schematically I'm showing it here. So this is all, that's how the graphene oxide membranes look like. And these are the path of mass transport in such laminar membranes. Once you have such membranes, the first thing what we did in 2014, when that okay, let's test this membrane. So first experiment was, we were new in membranes. Even my 2014 science paper was the first paper where I have used the membrane word. I was a semiconductor sensors and electronics engineer before that. So then if you see here, this structure, we put it in the YouTube like that, and then feed and permeate, and that's how we use this graphene oxide as a membrane. Now what happens in the membranes, especially when you see the pore size is so small, integrity of membrane is very important. If like to understand that the whatever is being permeated is going from the cracks or really going from the designed pores. So for that we have a very simple experiment, a mass balance. In one you have ethanol vapor, other one you have pure water. Then from the weight change you can see that from weight change you can see when you have water one, you see the change in the weight loss, and with ethanol no. Now it means the pores are only of the size of the water molecule. Even ethanol vapors cannot pass through pure graphene oxide membranes. Even ethanol vapors cannot pass through. With all our membranes, whenever we make flat membranes, this is the first test we do. This was the work we did, our very first work on graphene oxide. What we see here, that you see anything smaller than this size pass through the graphene oxide membrane, and anything above this one completely blocked from the membranes. This is a sharp cutoff, and this was the first time I think we reported a very sharp cutoff, and then I realized that the membrane engineers, they really like it, the sharp cutoff. We started from the hydrated radius of 3 angstrom to 6 angstrom. Once we see that this, from here we can also say that now these membranes, pure graphene oxide membranes, are that time cannot be used for the desalination, because sodium and chloride ions are really very, very small, but we can use it to block larger molecules or larger ions. So then I came to UNSW. Here I met my industry partner Sydney Water. Those days have wanted to develop new technologies to remove norms, and the first thing I didn't know about the norms back then. Then I asked them what's the size of norm. They said they're quite large. So I said yes, graphene oxide membranes can really block those norms. So from the basic principle we knew that norms will be blocked, but then our research was mainly on how to maintain the water flux when we block norms. And then we started doing those experiments. Here in the first way, I always do the YouTube experiment because this is the simplest one. It's Sydney Water's water and then deionized water, and then we measure the rejection, and then we do the same rejection here using the vacuum filtration, the flat membranes. That time everything I used to do with the flat membranes. Then we found that norms are always blocked using graphene oxide flat membranes, but if you really want to make membranes for the industry, we need to make the tubular membranes. And you see here, even with the flat membranes, we got water flux of 60 LMH, and with good stability also. So, and then this was, we can say, we converted a research curiosity into an alternative technology, but this was not enough for the industrial applications. So we made hollow fiber based membranes, graphene oxide coated hollow fiber membranes, and we invented a method how to make stable graphene oxide membrane on PVDF hollow fibers, and this is we filed the patent, and with that we can now make stable graphene oxide membranes on hollow fiber with a water flux of 150 LMH, and these membranes can work at atmospheric pressure. This is now we are very close to the for industrial applications. And here also, as norms are also like a negatively charged, and graphene oxide is also negatively charged, and that also helps us in stopping in controlling the fouling. So this is all like it's like a win-win situation to control norms in graphene oxide membranes. And for this our work, we are finalists in the AWA and UNSW Water Award. We are competing with the project which dealing with SARS-CoV, so we couldn't win it, but we are the finalist. And so this is, then we did a lot of work with the Sydney Water, which I cannot present now. This was like Sydney Water project is running for the last 5 years, and now at this stage we are now scaling up. We are setting up scaling up method. Then maybe in 2 years, 2 to 3 years, if all goes well, we will be using those membranes in the plant. Then for the graphene oxide, if we don't change the morphology, and then that's it, we cannot do any membrane applications. So we thought of playing with the porosity of graphene oxide membrane. That time I knew that okay, making the smaller would be difficult, so let's make it larger. So what we did, I used surfactant C-tab. Someone suggested me to use a surfactant, it can attach to graphene oxide nicely, and then we saw that here you see this is the intrinsic interlayer distance for graphene oxide, which is 0.86 nanometer. This is the porosity. In graphene oxide, the interlayer distance is the porosity for graphene oxide membrane. So this is 0.86 nanometer here, but with surfactant we could change it, or we can make it up to 3 nanometer. We know that okay, this is not going to block smaller ions, but we thought maybe we can still block norms, but and at the same time we can have higher water flux. So these membranes they show good results, but the stability was a bit questionable. So then we didn't continue that project of using surfactant modified graphene oxide membranes. Then we thought of changing. Then we were evolving with working with graphene oxide. So we thought of reducing the porosity, and if we could go for desalination, and then we did it using a hydrothermal method. We made RGO membranes, and we could get a porosity of less than 5 angstrom, and we did some conductivity test for sodium chloride, and these membranes are quite stable. And I'm not showing the real results because I have another industry project with an American company on removing salt ions and smaller chloride ions. So this is the quantitative results are that if you tune the porosity, you can really control the salt rejection. So this was reducing, we did enlarging the porosity and then reducing the porosity, both we did. And when we saw that graphene oxide, really when you heat it in different situations, it can give different properties. So then we did more literature survey, we came across these two papers. One says that if you anneal graphene oxide, there was a very nice article in Nature Chemistry from MIT group. They say that the composition of the graphene oxide will not change. However, the graphitic regions will be larger. But however, the other paper is also from Tsinghua University Hongwi's group. However, they say that they can see the graphitic areas are getting larger, but also see the composition changing. So we thought of doing both experiment in our both these experiments, repeating it. We found that, and the objective was if we can enlarge the graphitic domains, because you know the graphitic domains offer frictional flow of water. So then we can change. We can also reduce the porosity and have a higher water flux. Then we conducted some experiment in that, and we did extensive TEM studies. Like this is 1.5 years of work. We anneal those graphene oxide, just pure graphene oxide. This is the day 0 sample, means day 0 means not an anneal sample. So this is in the vacuum, and this is in the air. Different conditions. One was this is air was the Nature Chemistry, and this is like the Hongwi's group in Tsinghua. We see that in both the cases, the graphitic domain size, this is the image software. We did a lot of extensive TEM study to see the graphitic domains. We see here in this one, we can change the size of graphitic domains from nearly the, this is day 0 is the yellow one. So you can say this is the last time you can see this yellow one here, from 20 nanometer square to more than 200 nanometer square, the graphitic size of graphitic domains. And here in this case, in the vacuum, which also both of these techniques, they keep the functional groups intact. The concentration of functional group doesn't change much. We did NMR study for that, then we sort of TM studies more to see the graphitic domains. And here the vacuum one doesn't give more large domains of the pure graphene, whereas the air annealing, all 80 degrees centigrade, gives graphitic domains from 20 nanometer graphitic domains in pure graphene oxide to 200 nanometer square in air annealed graphene oxide. And if you see here, so this is the day 0 and day 14. So the blue ones are the large graphitic domains, and here also we did then abbreviation character TM and more HRTM. So see these are large graphitic domains here. These are large graphitic domains here. These are the mixed ones, but still we need to do more work on this direction to make it very large. If we can make highly reduced graphene oxide, or we can say even if we don't change the functional groups, if we can have higher graphitic domains, this will have advantage. It's like see pure graphene laminates, you cannot make pure graphene laminates because it will not be laminated structure because they don't have the functional groups. Here what we are doing, it's like in the beginning you have a graphene oxide flake with 10 legs. Now you are having graphene oxide flake with only 2 legs just to sit on top of each other, and then a large graphitic domain to have a higher water flux. We did this work, and then when we did this work, this was very good work. And if you see in this TM, we saw the single atom, the Fe. We intercalated Fe ions after that. In this one, what we see here that we did the water flux experiment. We found that whatever we thought that if we enlarge graphitic domains, we'll have a higher water flux. It was not true in our case. And so it's because then we did simulation study, because in principle it should be higher water flux when we have large graphitic domains. Then when we did simulation results and some theory, it suggested that okay, the water transport is governed by 2 things: the water diffusibility or the graphitic domain. So, and because when we are reducing it, you see here the interlayer space is also decreased. So now what is happening here, when we are heating it for a longer time, see 10 days one, the interlayer space also going down, right? So now let's say in the pure graphene oxide, let's say 5 layers of water molecules can travel together. Now only 4 layers of water molecules. They will be moving faster because of the graphitic because of the frictionless flow of the graphitic domain. But since the porosity is also reduced now, so the water flux is less. There are 2 competing factors here. One is the fast transport of graphitic domains, but on the same time we reduce the porosity, so this is allowing less water molecules to move parallelly. So this was not it didn't work according to our plan, but still we need to do more research to make. Now the next phase is to make the graphitic domains much larger, so that we can then the effect of interlayer space can be reduced. Now we see the effect of reduced interlayer space is dominating and compared to large graphitic domains. So it needs more research in this direction. And then what we did, we have a very good catalyst group at UNSW. They said that if you could reduce graphene oxide, let's use it for catalyst. So we collaborated with Professor Rose Amar's group, and then we see that this is, when I say day 0 means the pure graphene oxide, and this is 14 day means the most reduced graphene oxide. Here we see the HER is improved. So this is the worst HER OER performance. This is the best HER OER performance. And then we see that okay, when we do it, it improves a little bit. The catalyst properties of graphene oxide improves a little bit when you the anneal samples due to conductivity change, but Then when we introduce some single atoms into graphene oxide, like we used Fe in this case, the performance is huge change. You see here, from here to here, this is the best performance here. And now as we see here, when you have no iron in graphene oxide, the performance is improved because of its conductivity driven, because the conductivity is higher now because of high graphitic domain. But when we introducing Fe, the mechanism change. Now Fe plays a crucial role. So then, but if you further anneal the Fe geomembranes, the performance deteriorates. So you can say here, this sample, which is the best electrocatalyst what we made here, it shows it is as good as the iridium oxide in the OER performance. It's 360 millivolt here. So this is as good as the commercial benchmark, which is iridium oxide. And also, you know how we made this one? Just we mixed graphene oxide and FeCl3. We didn't even heat it. So now this is just by mixing and with mixing and then stirring the solution, we can get a electrocatalyst, a photocatalyst, which is as good as the commercial benchmark. So this is the another very nice application of graphene oxide. In same graphene oxide which we are making for membranes, shows excellent performance in when we use it for the catalyst. Okay, the other application was because we know that the graphene oxide absorbs water in a very high rate. It loves water, so we thought, can we replace silica gel, which is a commercial benchmark for water absorption. We did some work. You see, this is graphene oxide and this is silica gel. See, graphene oxide outsmarted is completely outperforming silica gel at 25 degree of water absorption, and it achieves 90% of absorption in 10 minutes, and silica gel needs 500 minutes. And the regeneration cycle is shows the same water absorption performance up to 10 cycles. And now this work is now has taken a different scale. Now we got an industry partner for this one, which I cannot discuss more work with. Now we have, our performance is now much better than what I'm showing it here, and this desiccant will also be very close to being commercialized using our industry partner Vessi Water. And you see here, and one good thing about it, that it regenerates around 40 degrees. So this is all, it can show that it can be used for our athletic wear, and we are working on that direction also. For these applications, we're planning to make incorporate graphene oxide, which will be in soles and in the clothes, so that it will absorb the moisture. And because graphene oxide absorbs moisture, so we did some experiments with the industry partner SVSR. Can it absorb H2S gas? And we didn't publish these results because this was industry projects, and we found that graphene oxide had a very good absorption for H2S in addition to H2O molecules. So it has two applications now, for desiccant for moisture absorption and H2S absorption for sewer applications. Okay, so this was graphene oxide for water for absorption, and I never worked on gas separations before, so we thought, can we use graphene oxide membranes for gas separation? But I know that the most of the gas molecules are smaller than the cutoff of graphene oxide membrane cutoff. So we knew that pure graphene oxide might not work, and it will not have a better selectivity or permeance for better selectivity for if we change the gas molecule. So we thought we can make it, we can change the mechanism of gas separation. Then what we did, we made a new class of membranes. We call them transition metal incorporated graphene oxide. Here again we used Fe. We incorporated Fe into graphene oxide, and here, and these membranes are made in ethanol because we want to have no moisture on the membranes. So, and we made flat membranes of Fe incorporated graphene oxide. We see the monolayer quality of graphene oxide, single atom Fe here, and nice distribution of Fe throughout the membranes. And these TMGO membranes, then we use them for the gas separation in the flat membranes form. We haven't done the tubular membrane work on this one. You see here, when we have Fe atomic percentage from 0 to high, it shows very high selectivity of 97 for around 2%. Optimized value of Fe is 2%, and the permeance value is also very high. In the beginning, we couldn't. We wanted to do CH4CO2, but in the lab conditions, we couldn't find the CH4 source at that time. We published that paper in Advanced Materials. This is, I think, for any graphene oxide-based material, this is the benchmark. Yeah, here you see, this is this is all normalized values at the same pressure. So these are MOFs and graphene oxide, our membranes, so this performance for selectivity and permeance. So these membranes have huge potential for gas separation, but N2 is not very separating. N2 is not challenging, not very useful. So we thought of doing CH4, and from here we can say that yes, we can use graphene oxide membranes, even the gas molecules with similar kinetic diameter, not much difference, because when you do liquid separations, you can find ions or molecules of different sizes to check the separation behavior in liquid medium, but in gas in the gas medium, it's very difficult to find molecules of very large size difference. So we can say that yes, by incorporating Fe, we can have different adsorption sites, because Fe adsorbs nitrogen much faster than CO2. So, and then it absorbs CO2 and then moves faster in the capillaries. And that's why it makes the selectivity is 97. And we are going to use this for other gas mixtures. And not only that, we are also now incorporating other transition metals like chromium, cobalt, nickel, and other in graphene oxide, and see how it performs, how it behaves for different gases. From there, we have industry project with tires, because tires, when you paralyze them, like you can say at around 500 degrees, they give CO2, CH4, and CO. So we thought of using our graphene oxide membranes for the gas separation for the real industrial applications. I got 2 projects from Tires Towards Australia, and from there, if you see, we are getting good CO2, CH4 selectivity. It's very initial results. And we are doing more work now. We're trying to change the transition metal from Fe to other elements. And you see here, and we also want to use it for the biogas, because biogas also have CO2, CH4, and the tires also have CO2, CH4. So this is again a win-win situation for multiple applications. And here, and the biogas, it has more potential for the biogas. Here you see biogas have hydrogen sulfide also, that percentage in that way, and we have already shown that graphene oxide can absorb H2S. So what we are trying to do, same graphene oxide membranes, we use it to separate gases coming from the tires and separate gases coming from the biogas, and will absorb H2S also. This is another industrial project which I'm only showing the basic results. So here, if you see here, the graphene oxides in general have some multiple applications, like water purification. We use it for water purification. We use it for desiccant applications, and the desiccant application is now really, we have done a lot of work on that. Very soon we will have a press release on that, our new success, and we use it as a catalyst. It is as compared to the commercial benchmark, and when we are doing gas separations, it's also showing excellent performance. And all these work, they fit into the national science and research priorities of energy, water, and advanced manufacturing of membranes. Okay, with this is all about what I wanted to show, because this, but I'm open for the questions. And this is my team, and I don't have many students and postdocs, but all my research students work very hard. I recently Sui from UNCH's group of Sydney Uni, she recently joined. She is the only authenticated chemical engineer in our team. We are all material scientists otherwise. And my industry partners with Sydney Water, we are now scaling up. It's a really a big project now. Sydney Water have already invested more than $500,000 in this one, and we are scaling up with we make kind of, you can say that we're making like 2,000 membranes together. In our lab, in my lab now, then we will use this membranes for the client. With SVSR, we made graphene oxide to absorb H2S, and with Vessi water, we are making graphene oxide desiccant. With GDTC and TSA, this is like a linkage scheme, but for the TSA, not from the ARC. Like the industry, we get a tire, we get some money in the initial seed funding from GGTC, and then we we analyzed the gases coming from the tires, and the tires towards Australia. We're using our graphene oxide membranes to get pure methane from the tires, and also what we have done that we have used the pure methane to make graphene using a CVT system. So these are all my industry partners and my collaborators, and you see here all are UNSW chemical engineering. When I came to UNSW, I started collaborating with Professor Leslie, then Professor Smith. Professor Vicky Chen helped me a lot in understanding the basics of membranes and making the hollow fiber membranes. I'm working on Professor Korush Kalanta Jade and gas separations and intercalation, and Kumar is now my long-time collaborator for simulations. He is the researcher, and for this the MIT group who made this structural evolution in graphene oxide by mild thermal annealing, and now we are using graphene oxide for catalyst. So I'm collaborating with Professor Rojamal and Dr. Dayan. With this, I thank you, and if you have any questions, I'll be happy to answer.
Thanks, Rakesh, for this wonderful talk. Particularly, it's very amazing to see actually so many promising applications, for the graphene oxide material. Now we have a time, I think, for questions. I think we have already a number of questions in the chat box, and I will read one by one. For someone who wanted to ask another question, please put into the chat box. Let's start. I think the first. This question is asked by Sanjay. His question is, graphene is also swell in water and might delaminate during water-based application. Does not it delaminate during water treatment?
Okay.
Very good question.
Yeah, swelling is in graphene oxide. Swelling is a problem, but now using using the mild thermal annealing method, we have controlled the swelling. Now, if you do the mild thermal annealing, and then it doesn't swell anymore, and also our the patent we have we use a cross linker to PVDF, and then it doesn't delaminate. It's very strong, and we check the stability for many methods, and it's now in the lab scale is very strong. Maybe when we do a huge amount of water, that also we can see. But now in the lab scale, all our tests show that it's very strong. And if you only have on a PVDF substrate, it might come off. But if you use a cross-linker, it's very stable.
Yeah.
And swelling is also being controlled using mild thermal annealing. I think the graphene oxide researchers, I think Professor Siwang Group also, you also did some mild thermal annealing work, right?
Yeah.
Yes. I think the mild thermal annealing is going to be a new direction to use graphene oxide for other applications. It gives further stability to graphene oxide membranes.
Yeah. I think at this moment, a number of very useful strategy have already been reported to overcome the swelling problem of the graphene oxide-based membrane.
Yes, and we are also doing some work with, I think from the Manchester group, they published a paper in Nature Nanotech about using epoxy.
Yes.
Right?
Yes.
Even if you see in my science paper, in the last line in the conclusions, we wrote that our next work will be controlling the interlayer space by mechanically controlling it. Right?
Yeah.
Then they did it in the Nature Nanotech paper that this is now by epoxy. We are also doing the similar work in different way. That we want to control the swelling.
Yeah.
Yeah.
Good. And the second question actually is from me. Rakesh, I saw your TMGO membrane.
Yeah.
Showed I think a fantastic performance
Yeah.
I'm just wondering, could you explain a little bit more the separation mechanism?
Yes.
Whether it's based on the size exclusively or it's based on the
I think it's not,
the chemistry functionality on the membrane surface.
Yeah, it's not size explosion because it's more about what happens that the Fe, the sides, they absorb this N2 faster than CO2. So it absorbs. It's like a diffusion driven. It's not size because the size is nearly same.
Yes.
So so that's why if you do only graphene oxide, so I think a lot of other people also have studied Fe for in other systems. Right?
Yeah.
We say that Fe absorbs N2 faster, and then once it absorbs faster, then it travels faster within the capillary. So there's a diffusion control mechanism.
Yes. Yes. Yeah.
Not like the basic nuts and the other mechanisms, right? Because their sizes are very small.
Yes. Yeah. I think the next question, let me just say, is because a nice presentation is a hero. In your point of view, what are the best approaches to evaluate the macro or nano crack or the pinhole across the graphene oxide membrane? And before and after testing, the testing.
Okay, I think there was more question before that. When do you think the material will be commercially available for use, right? I think graphene oxide is already just after your question,
Oh yes, I apologize.
Yeah, it's okay. It's okay. I think graphene oxide is commercially available. Now the price is higher, but it's the good quality. I use the graphene oxide from my only one supplier because I don't make it in the lab now because we use it a lot. We use it a lot, right? I have a supplier in Japan. I always get the one source. So and then I think it's commercially available now. It's a bit expensive, but sooner and but for the
cheaper and cheaper.
There are some cheaper suppliers also, but sometimes it's all about trust. Right? Maybe they're already good, but I have been using always graphene oxide is commercially available. Even I buy it a lot, like in 10 liter, like in half a kilo every year, like that. And there was more question like, do you prepare the geomembrane without a support? If support is used, then we use it for support, PVDF support always. We can make it without a support also, but that method is very we can use it like if you see Rahul Nair's 2012 science paper, right? What they did, they made because they were also not a membrane people before, right? So they used to coat graphene oxide on the copper and then remove then etch away copper using the acid, but we always use it on a support. Next one is
Albert.
Albert,
a question. Is Albert from the Sydney Water?
Who?
Albert.
No, Albert is, I don't know. Maybe the nice person. Okay. Nano and pinholes. That's what we need. That's the integrity of membrane is very important. So whenever we do it, before and after test, we always have this vapor evaporation test, and that's why it took us 3 years to have a patentable method that provides extra stability and no physical holes to graphene oxide membranes. Yes, and if you make them very thin, like few hundred nanometer. So in my research, I always use around 1 micron. Right? Now as we are evolving, now we can even make 500 nanometer very continuous films with no pinholes. But if you go below this, this problem will be there. So, but in all my research work, I showed it's all about 1 micron thick graphene oxide membranes. Okay, this is the. I think this is the cross-linking. I think it's still confidential.
Okay, we can skip this question.
I can skip this, and then Regarding scaling of
Question from
geomembranes,
Sean.
I was wondering, Sean, okay. Regarding scaling of geomembranes, I was wondering if you could share what membrane surface area, module configuration, and yes, we have it a lot. I think I can have a meeting with Sean sometime, right? And we can discuss these things.
Yeah.
And I think he's in Sydney, so I think we should visit him sometime. Right?
Yeah.
I have most of the data asking in the question. I have it, so I can visit him and we learn from his experience.
Sure.
Because in the beginning, like when Vicky Chen was here, she helped me a lot in understanding the membrane basics and the parameters. Now I have nearly everything whatever Son asking, so we have answers, so I can talk to him and discuss. Thank you, Son.
Rakesh, the next question is still from the Albert.
Yeah. Do you think we need to do a compaction of geomembranes prior to collecting the water flux, especially for those which water supported the polymeric? We always test these membranes before, but we cannot test all the membranes, right? Like one batch, we test the geomembranes for their any mechanical cracks, right? So, and then I think we tested, but one batch, not all the membranes. How much reduction in water flux to observe after cross-linking? No reduction of water flux. So this is to for the stability and without compromising the porosity. So water flux only depends on the porosity. Or if you don't change the hydrophilic behavior of graphene oxide, you need functional groups there. Subtract water molecules and make this laminated structure, or cross-linking will not have much effect on water flux, depending on the concentration of the cross-linker we use.
Yeah.
Okay. Albert is from Deakin Uni. Can you use existing commercially available membrane and spray coat graphene oxide to improve them? Yes, we are doing it. Yes, we are doing it, Dharma. We are doing it because the commercially available membranes are very good support.
Yeah.
So we are doing it, and that's what even all of our membranes are coated on. But we don't do spray coat. The spray coat is not very. I was not successful in spray coating because I don't know how to make the spray coating for very large area and maintaining the uniformity in the thickness. So we do it. Most of our membranes are vacuum, or either the pressure using the dead-in cell or using the vacuum filtration.
Do we have any more questions? Maybe I can ask one more. Rakesh, actually a lot of researchers, they use the graphene oxide as a nanofiller, put the graphene nanosheet into the polymer membrane matrix, try to improve the membrane performance, either the flux or selectivity. Could you comment on this? I think strategy, because a lot of people they argue, this method is quite easier, to scale up.
Yes.
Compared to the laminar membrane.
Yeah. I think even when I talk to the real membrane experts, right? Like you, Professor Wang, and Professor Vicky, and the Matthias Ulbricht in Germany, right? The real they don't like much graphene oxide, right? They are the real membrane engineers, real membrane. So it's always the polymer membranes are very stable, right? So if you use graphene oxide as a support to have a higher water flux and tune the cutoff size, right? that can be a good strategy. That the polymer membranes might not give you a nice cutoff, so we can use graphene oxide to get a cutoff in the size in the membrane for rejection. But I haven't done any work on this one yet, because what we do is mainly pure graphene oxide.
Yeah.
But I think it's a for a scale up, for the large scale, that can be a way. That can be a way for multiple applications, like for the gas separation. If you do flat membranes,
Yeah.
that can be a way to do it.
We have 3 more questions.
Yes.
The first 2 is from Quentin.
Yeah. What is the interaction between single atom Fe and GO? How is the Fe is very stable there, but you see the Fe in Fe GO membranes we haven't used for the liquid yet, separation yet. So and we used it for the electrocatalyst. We did it before and after. Our characterization said it's stable, and they are just Fe, the atomic single atom there. Right? This in the atomic form. That's why it was a better catalyst. And now we want to, because this FeGO is really it's amazing. It was so good for the gas separation. It's so good for the this one for catalyst. So now in our lab we are going to use it for real liquid medium. You see if Fe stays there, because if it's atomic, if it's not bound, it might come off. So that's, we haven't done the liquid experiments using FeGO yet.
Question: would the Fe be oxidized?
No, it was atomic.
When it is exposed to oxygen?
No, it was not. It was not oxidized. We are still doing it, because when we are doing with the catalyst group study, there were questions that and this one even our HER performance when it was going down in heating.
Yeah.
Because you see, if you see the when we are doing the HER performance on only GO, the heating was making it better, but when we had Fe there, the heating was making it worse with Fe. So that question came in our mind. Maybe now the Fe is oxidized, so we haven't done any study to confirm it.
Okay, all right.
So that time we thought, okay, now we will do that study, because that was the first thing came in our mind when you see in my plot. Even this paper is on archive now. We submitted for publication. It's on archive, because when we have FeGO, and then when we heat it, even 80 degree, the catalyst behavior, maybe it get oxidized, but we didn't test it yet.
All right.
Yeah. Doing some analyzing would functional groups become cluster. Yes, that is the work. You see the nature chemistry and Hongwi's group. They say that what happens when you do a controlled annealing, the functional groups don't go away from the graphene oxide, but they make a self clustering.
All right, so they move closer.
Yeah,
right?
they move closer. That's what we did in our TM study. Also shows that our NMR study shows that the concentration of groups don't change. When we see the concentration of the groups do not change, but the graphitic area is larger, it shows that they make clusters.
Yeah.
We call it self clustering, and we in our archive paper we have all the results there. Yeah,
all right.
So this is self clustering, and that was our aim, that okay, we can make self clusters that will make graphene oxide stable, and the graphitic domains will have a larger flux. But it was good for the electrocatalyst.
Because it's quite interesting, right?
Yeah. This is a very interesting work, the Hongwi's group from Tsinghua and the nature chemistry one. So, but they didn't do the TM study.
Yeah.
Based on the basic characterization. So that's what our first thing. Okay, let's see if we have a larger graphitic domains. Let's do TM. So we really spent 1.5 years to do TMs in different labs, because the high sensitive TMs are not very easily accessible. So, and we really did a lot of TM study to see the large graphitic domains, and we finally saw that.
Right.
Yeah.
Thank you.
Any more question?
Yeah, there's one question. During cross-linking, functional group GO is consumed during reaction, and interlayer space is also decreased. Yes, this is that's what we are what we want to do. See what is happening now. In the graphene oxide, the interlayer space has a huge role for water flux. How many layer of water molecules can travel together? Now, when we are decreasing, when the size is decreased, now the water flux is low. But if we can trade off, if we can have a trade-off of large domains, which will then we can have this, we can decrease the size and have the cutoff towards the left in salt ion size, and then also have the same water flux. Otherwise, whenever we reduce the size, water flux always decreases. So the only way is to have reduce the porosity or reduce graphene oxide and have a large domain. It's like a carbon nano. It will become like a carbon nanotube with like half angstrom diameter.
Yeah.
Yeah.
And the normal question, I think now we are quite close to our 12 o'clock. Rakesh, could you stop sharing?
Okay. Thank you very much.
Yeah, thank you. Thank you for your nice talk and maybe share with